Bam! Mr. Tarrou. In this video, we're going to do a four-part question that is going to be involving, well, A, finding the second derivative implicitly. B, we're going to be determining a relative, if a relative max or min or neither exists at a point for a function. We have a question about analyzing the limit of a function at a given point. And then in part D, we're going to be estimating a function's value given, well, a differential equation using Euler's method. You're going to find timestamps to jump ahead to any of these four parts if you like. You can find a link to the apcentral.college board website where you can find years and years and years of past AP exams, at least free response questions, the marking scheme, and the master scores commentary to learn where students either earned or did not earn those points, because we're trying to get that college credit by passing this test, or maybe you're just trying to pass your high school or college calc class. I hope this helps. You'll also find links to my playlist that I've created over the years. Okay, so we have here, consider the differential equation dy dx is equal to 3x squared minus 1/3 y. So we already have basically a first derivative given to us. And using that differential equation, which just simply means you have an equation with a derivative in it, we're going to find the second derivative with respect to x in terms of x and y. They're kind of being kind. I'm being kind to you here and saying, hey, I want my answer in terms of x and y. What that really means is that I don't want a second derivative with a first derivative notation in it, and that's exactly what's going to happen. With this differential equation, we have the variables of x and y mixed in together on the right-hand side. So we're going to find that second derivative using implicit differentiation. Remember, we are taking a derivative with respect to x, not with respect to y. Make sure you pay attention to that notation, because I could simply, well, give you a derivative, say dy dx dy, and we're taking a derivative with y instead of with respect to x. If I can talk correctly. Okay, so second derivative of y with respect to x is equal to, we're going to bring that power of 2 down and have 6x, reduce that exponent by 1. Remember that we're taking a derivative with respect to x, and I'm just going to do this for teaching purposes. I'm going to finish that chain rule that, inside that power of 2 we have a variable of x. So 6 times x to the first, finish the chain rule, the derivative of x with respect to x. Of course, that's going to cancel out. But on the second term here, we're going to bring that power of 1 down and have negative 1/3. Y to the 0 power is just 1. And don't fall for that first point of a common error that students make with these problems. Don't leave it just negative 1/3 as your last term. We're taking, again, a derivative with respect to x. So it's going to be negative 1/3, finish the chain rule, dy dx. And here we have a second derivative with a first derivative notation in it. We never want that as a final answer. So now we're going to take our 6x, that's just going to cancel away like we said, minus 1/3. We're going to take out that dy dx, that first derivative notation, or replace or do some substitution with what it's equal to, 3x squared minus 1/3 y. Do a little distribution. We have 6x, we have negative 1/3 times 3 is negative 1, x squared, negative times negative is positive, 1/3 times 1/3, of course, is 1/9 y. I'm not writing an equal sign on each line of my work because if you're prepping for your AP test, that's just opening the door to all kinds of possible linking errors and you not earning maybe as many points as you really deserve, because they have to stop grading at what they call a linking error. So our second derivative is equal to 6x minus x squared, or negative x squared plus 6x if you want to write those in decreasing powers. But then, of course, you have this variable of y popping in anyway, which kind of just comes out of nowhere, at least when you're thinking about writing, say, polynomials with decreasing powers on your terms. Our second derivative, 6x minus x squared plus 1/9 y. Part 2, or B, coming up right now. Part B, we're going to let y equals f of x be the particular solution to the differential equation whose graph passes through the point negative 1, 9. Does the graph of f have a relative maximum, a relative minimum, abbreviated this for space, or neither at the point -1, 9? Justify your answer. Regardless of whether you're told to justify your answer to anything on a calculus test, you should just assume the answer is, I need to. Okay, so relative max and min. If you are asked to identify whether a function has a relative max or min at some given value of x, or in this case because we're talking about an implicit expression or equation, we have the entire coordinate, first thing you should go to is the first derivative test. At this point, is the first derivative changing from negative to positive, indicating a relative minimum, or is the first derivative changing from positive to negative, indicating a place where you have a relative maximum? And of course, you're going to find those critical values where you test for that sign change on the first derivative, where the first derivative is either equal to 0 or undefined. But with this particular question, see, we already were told and asked to calculate the second derivative. So you can also identify a relative extrema using the second derivative test, which is if the first derivative is equal to 0, and the second derivative at that same point is greater than 0, indicating that your function is concave up, well then you have a relative maximum, minimum. And if the first derivative is equal to 0 and the second derivative is less than 0, indicating that the function is concave down, well then at that point you have a relative maximum. The neither part. If the first derivative isn't equal to 0 or undefined, then there's no possibility of you having a relative extrema of any kind. So let's first go there and say, what is the value of the first derivative at the point of -1, 9? And I'm guessing this is going to be 0, otherwise it's not a very interesting problem. Looks like a little bit like 91. Okay. We have 3 times the x value of -1 squared minus 1/3 times the y value of 9. We're looking at, I'm using equal signs when I told you not to for fear of getting some easy linking errors. Okay, so your first derivative is equal to 0. Good. If you have a few lines of work and you just wrote something a little bit silly in the middle, but then sort of unintentionally or unknowingly corrected that error on the next line of work, if they're just individual lines of work with no equal signs, then it's just scratch work. But if you put equals, 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 you're saying that basically that's a train of equalities, and if there's even one point in that chain where you've written an untrue statement, we have to stop grading at that point and call it a linking error. You said A is equal to B when they really are not, even if it was just a copy error and you corrected it later on unknowingly. That's where the grading has to stop. So this is really not a good idea. So you do all the scratch work and then restate your final answer. Okay, so at any rate, space. So our second derivative, again, at that point of -1, 9, since we already have that second derivative to work with, just plug it in. We have 6 times -1 minus -1 squared plus 1/9 times our y coordinate, which is 9. Don't do what I almost just did there. And that is going to be -6 minus 1 plus 1. So -6. Let's just make sure I didn't write something silly. Nope, actually my notes are silly because I wrote a 1/3 there. You know, see, copy error. At any rate, okay, so our second derivative is, well, -6, which is less than 0. Now at this point, you can't just write, you know, y or f of x has a something and just stop. You have to link your conclusion with the evidence that you are using. So at negative 1, 9 dy dx. It's even considered vague language to just say, I wouldn't even write the derivative or the second derivative. Dy dx is of that point, just to be super redundant here, is equal to 0. And actually, if I write this notation, I'll have to write that. And the second derivative at negative 1, 9 is less than 0. Therefore, you can just write that notation. Y has a relative what? If your first derivative is equal to 0 and your second derivative is less than 0, that means that function there is concave down. Therefore, you have a relative maximum at 1, negative 9. Part C coming up right now. Bam! Part C. We're going to let y equals g of x be the particular solution to the given differential equation with g of negative 3 equals 5. We're going to use that information to evaluate the limit as x approaches negative 3 of g of x minus 5 over 2 times x plus 3 squared. Now, it wouldn't be a very exciting test question if this just worked by plugging in negative 3, but go ahead and start to think that out in your head. If you let x equal negative 3, well, g of negative 3 is equal to 5, and 5 minus 5 is 0. Okay, no problem having 0 in the numerator, but then 2 times negative 3 plus 3 squared, well, that's 2 times 0 squared, which is, well, 0 again. This is illegal. Do not write that on a test, even though if you look at my wonderful video for L'Hopital's rule, I did use that that notation initially, but that really is a form of indeterminate, and this is truly not going to be the answer to this question. That's considered linking error. AP will stop grading. Evil, don't do that. What they really want you to do, well, you can, as of this video, I've been taught by my trainers that you can write that this is in the form of 0 over 0. Thus, you can, you've passed the condition check for being able to apply L'Hopital's rule. What AP really wants us to do, though, is to show the analysis of that limit both in the numerator and denominator separately. And we have the limit as x approaches negative 3 of g of x minus 5 comes out to be 0, as I verbally stated previously, and the limit as x approaches negative 3 of our denominator, again, comes out to be 0. You want to write that out. You're showing your work as instructed, and it's also your conditions check that both the numerator and denominator have a limit of 0. That is a form of indeterminate that allows you to apply L'Hopital's rule, which is where we take the derivative of the numerator and denominator separately and try and re-evaluate. Now, when you get this form of indeterminate, it does not guarantee that a limit exists. It just tells you that you have work left to do. So, L'Hopital's, we're going to take the derivative of the numerator. So instead of g of x, we have g prime of x. The denominator, we have the derivative of 2 times the quantity of x plus 3 squared, comes out to be 4 times x plus 3, and then try and reevaluate. Well, we basically were introduced to a new variable, but we said let y be equal g of x be the particular solution to this differential equation. So we're going to plug in that point of negative 3, 5 into our first derivative, our differential equation here, and see what happens. So we have the limit as x approaches negative 3 of g prime of x is going to be equal to 3 times our x coordinate of negative 3 squared minus 1/3 our y coordinate, which was 5, over 4 times x plus 3, well, x is negative 3, so we have 4 times negative 3 plus 3. That's going to come out to be equal to 27 minus 5/3, so we're looking good so far. We're going to get a real value out of the numerator, but the denominator is equal to 0. Now remember, we're looking for a real limit for not g prime of x over 4 times x plus 3, but the limit as x approaches negative 3 of g of x minus 5 over 2 times the quantity of x plus 3 squared. And this is not a form of indeterminate. It's a constant over a denominator approaching 0. Now, if we were analyzing the limit of this expression, then I could say, hey, do you want to determine if this actual answer is, infinity or negative infinity? Because thinking about asymptotic behavior, if you have a two-sided limit where x is approaching some constant c, and both the left and right-hand limit is going to infinity or negative infinity, you can say that the limit is either positive or negative infinity, which is indicating that there is no real limit. But this is basically indicating here that it just simply does not exist, okay? The limit as x approaches negative 3 of g of x minus 5 over 2 times x plus 3 squared equals does not exist in this case. Not really very exciting. That's because I'm trying to change these questions a little bit to make them my own, make up some new numbers, create new expressions, and this one just didn't really work out to be very nice. But that's okay. That's the whole point of working through this indeterminate form. When you have a limit which gives you a form of 0 over 0, yeah, usually in our textbook, L'Hopital's rule ends up giving you an actual answer after you apply L'Hopital's rule once or a couple or 3 times, but it doesn't mean that a limit has to exist. Part D coming up right now. It's the last part. We're going to let y equals h of x be the particular solution to the given differential equation with h of 0 is equal to 3. Use Euler's method starting at x equals 0 with 2 steps of equal size to approximate h of 1. And if you're not familiar with Euler's method, hopefully you are, but they're basically saying if we were to solve this differential equation, which for our intents and purposes we don't know how to do, but if we could solve this and find some function h of x, that graph would have some kind of shape, whatever it may be. And this differential equation is describing the slope of this function h, basically everywhere that h is differentiable. And we're going to say, hey, we know that at the x coordinate of 0, h is equal to 3. So we have this point of, now this doesn't match what's necessarily going on, but there's some point at 3. And we can't really truly know exactly what h of 1 is equal to because we don't really know what function h is. We can't solve this differential equation, but we can use tangent lines and say, hey, we're going to find this tangent line, this, using the derivative, using the slope, at 0, 3, and we're going to make a small step, well, to this point of, if we're taking two equal-sized steps between 0 and 1, each step is going to be 1/2, we're going to move over to the x value of 1/2 and just find out where the tangent line is at that point, or at that x coordinate of 1/2, and let the tangent line approximate the value of the actual function h. And then at that point, we're going to go back to our differential equation, which is describing the slope of h, and find out, hey, okay, at the x value of 1/2, function h takes on this approximate y value. Now, while the y value is approximated, we have a function which is going to give us the slope. And so then we're going to analyze the slope at our estimated point, and then off of that, and we see our graph is dropping here, come up with another tangent line, and then step over to the x value of 1 and estimate again where is function h at 1 using this next tangent line that we found using the previous estimated point and the slope from the differential equation. That's what Euler's method is. It's just a sequence of tangent lines and approximations with those tangent lines to approximate some function given a differential equation and an initial point. So, little mini micro Euler's method lesson there. We don't need the second derivative anymore, unless you wanted to analyze whether your linear approximation was an over or an underestimate. One step off. Okay, so at the point of 0, 3, what is our slope? dy dx at 0, 3 is equal to 3 times 0 minus 1/3 our y-coordinate. And this first part was made out to be relatively neat. We have our slope is equal to -1. Now, you can abbreviate and kind of streamline this notation a little bit. Sometimes your textbook asks you to do a ridiculous amount of steps. Sometimes my textbook that I teach from had them do like 10, 15, 20 steps, so monotonous, of Euler's method, but we're only doing 2 here. So I'm not going to worry about having this 2 streamlined. I'm going to now use that tangent line. We have a point of 0, 3 and a slope of -1, and I'm just going to use sort of point slope form. We have y minus the y-coordinate of the point, 3, is equal to -1 times, now we're taking basically a half step off of x equals 0. So it's going to be 1/2 minus the x value of this point, which is 0. And if you're taking equal size steps, you don't really honestly need to do sort of like a x sub 1 minus x sub 2 or something like that. Should always work out to be a difference of 1/2, but you do need to do the y minus y sub 1 equals m times x minus x sub 1 and actually calculate that step if it changes through your Euler's approximation. So we have y is equal to -1/2 plus 3 over 1. Find a common denominator, and we have y is equal to what? 5/2. So now we're going to go to step 2, where we have an approximated point for function h using our tangent line. Our new point is a half step off, so it's 1/2 and the new y-coordinate we just found of 5/2. And while we have a point, we don't have a slope. Oh, by the way, is this a reasonable first step? Well, actually, I'm starting at my second step, but is this point a reasonable answer for the end of my first step? Well, off of the point of 0, 3, we did get a negative slope. So if we step to the right a half unit, we should expect our y value to shrink a little bit, and we did go from a y value of 3 to a y value basically 2.5. So now we need to know what the slope of the tangent line is at this approximated point. So dy dx at 1/2 5/2 is equal to 3 times 1/2 squared minus 1/3 times 5/2. We're looking at 3/4 minus 5/6. We need a common denominator, so we're going to multiply by 2. Well, I'm saying multiply by 2 and by 3, but 2 over 2 is 1 and 3 over 3 is 1. So we have what? 9 minus 10, so -1 over 12. Stepping off a half unit over to the right, we have that, and using the point slope form of a line, no reason to streamline this for only 2 steps, we have y minus y sub 1 is equal to m, -1/12, times x, a half step to the right of 1/2 is 1, minus, well, x sub 1. So we're looking at y is equal to 1/2 minus 1 minus 1/2 is 1/2, times negative 1/12 is negative 1/24 plus 5 over 2, multiply top and bottom by 2, 12. And we have y is equal to negative 1 plus 60, or 59 over 24. Thus, or therefore, based on these two steps of Euler's approximation, we have that h of 1 is approximately, this isn't exact, it's based off of tangent line approximations, 59 over 24. I'm Mr. True. Bam! Go do your homework.